All right, let's go ahead and continue here. Now we need to talk about the difference between molecular equations and ionic equations, and then how to write a net ionic equation. Again, hopefully you guys, this comes back to you pretty quickly from last year. But the molecular equation, we're basically just talking about, we're writing out the whole equation the way that we would normally write it, okay? We're writing these as though they were compounds. So we're writing AgNO3 as though it were all together, KCl as though it were all together, and so on and so forth, okay? Now we know that's not really truly the case when something's in an aqueous solution. Okay, but let's practice just writing a molecular formula here for our molecular equation for something that is a double replacement reaction, okay? So we've got, we want to predict the identity of the precipitate that forms when solutions of barium chloride and potassium sulfate are mixed. Okay, so we know first off the barium's going to go with the sulfate because the positively charged always goes with the negatively charged, the cation goes with the anion, and then the potassium's going to go with the chloride, okay? Now, we should be able to figure out which one is not soluble right away just by remembering which ones never, we should be able to figure out which ones are soluble right away by remembering which ones never precipitate. Okay, and the alkali metals never precipitate. Potassium's an alkali metal. There's no way that KCl is going to be a solid. Okay, it's not going to be the precipitate. So it's got to be the barium sulfate. Even without knowing any of the other rules, a lot of times if you remember a couple of the basic ones, then that will help you. So barium sulfate is going to be our precipitate. Now, you may have had to think about that a little bit more here. Barium's a 2+ charge. Sulfate is a 2- charge, so when those come together, it's a 1-to-1 ratio, barium sulfate. Okay, now they want us to write the balanced chemical equation for the reaction. So we've got BaCl2 aqueous plus K2SO4 aqueous yields KCl. It's going to be a 1-to-1 ratio there, and that's still aqueous because potassium never forms a precipitate with anything, plus barium sulfate, BaSO4. And that is a solid. That's an S. Okay, so then we just have to balance this thing, and usually double replacement are pretty simple to balance. There's 2 potassiums. That's the first thing that I'm noticing here. 2 potassiums, we need to put a 2 right here in front of the KCl. That also balanced our chlorides because there's 2 chlorides on the left side. Now there's 2 on the right. Everything else looks pretty good, so I think we're balanced. So that's pretty simple. Now net ionic equation. Okay, with the net ionic, what we're doing here is we are writing these things out as they really happen. Okay, so when we've got AgNO3, okay, it's really not technically correct to write this as AgNO3. Now if we write aqueous, then everyone knows what we mean. But these things really are split apart in water because anytime you put an ionic compound into water and it dissolves, then it's going to dissociate. It's going to break apart into its ions, okay, because they are electrolytes. They're strong electrolytes. So really what we have here is Ag plus and NO3 minus, okay? So we're going to write down all of these things as they really are, okay? And then what we're going to do is cross out the ones that don't do anything in the reaction, okay? The nitrate is NO3 minus on the left side of the equation. It's NO3 minus on the right side. So we just cross those out, okay? The potassium ion is K plus on the left side. It's K plus on the right. Nothing changes, so we cross those out. But notice here, Ag, or silver, goes from Ag plus to being in a compound down here with chlorine, okay? So that actually did something. Something changed there. Something is different. Cl minus, the chloride ion, became a chlorine in a compound with silver, okay? And so those are the ones that do something. So when we write our overall net ionic here, go back. Basically, it's going to be this, Ag plus Cl minus yields AgCl solid, okay? And that's all you really have to put on those. On the AP exam, I don't think you even, if I'm remembering correctly, you don't even have to put the AQ there, the aqueous, because we're assuming that this is done in solution. If it's an ion, then it's definitely aqueous, okay? You can put it if you want to. So writing net ionic equations, you're going to write a balanced molecular equation. That's usually a good idea to do first. Dissociate all the strong electrolytes. Cross out anything that is unchanged, anything that doesn't do anything. Or those are called spectator ions. I think that was on the last page. Check. Yeah. Spectator ions. Remember, those are the ones that just sort of watch these things happen. They're kind of the creepy ions. And so we just want to get rid of those. So anything that remains unchanged from the left side to the right side, we cross out, and then whatever remains, that's what we write for our final equation. Okay? All right, write the net ionic equation for the precipitation reaction that occurs when solutions of calcium chloride and sodium carbonate are mixed. I'm going to move this up here because I need some room. All right, so calcium chloride, that's going to be CaCl2. And it's solutions of these things, so we can assume that they are aqueous to begin with. And sodium carbonate, that's going to be Na2CO3. Carbonate is a 2- charge, so it takes 2 sodiums with 1 carbonate here. And then that's going to form sodium chloride, NaCl. And again, sodium is an alkali metal, so it's never going to precipitate with anything. This is going to be aqueous still. Plus calcium carbonate, okay? And you just have to look at your solubility rules and see if calcium carbonate precipitates or not. They're not going to give us one that doesn't, which they also don't on the AP exam, by the way. And I'll try to remember to mention that in class as well. But they do not give you reactions that don't happen on the AP exam. So that's kind of nice. You don't have to worry about that. All right. So then what we have to do, and this is the part that takes forever, is we basically just have to break these apart if they're strong electrolytes, okay? Calcium chloride, CaCl2, that's an ionic compound. It's dissolved in water, so that's going to be a strong electrolyte. So this is going to be Ca2+, plus, see, I told you you don't have to do this in the AP exam, so I'm not going to do it. Write the aqueous for every single one. It's understood for the ions. So Ca2+, plus 2 Cl minus, okay, because when this breaks apart, every calcium chloride that breaks apart, there's 1 calcium ion and 2 chloride ions, okay, plus 2 Na plus CO3 2 minus, okay, so that's the balanced side of that equation. That gives us Na plus Cl minus plus, and then this part, this is not ionic, okay? This does not split apart into ions. Calcium carbonate is actually a solid at the bottom of this solution. So we're going to keep that as CaCO3. We do not split that apart, okay? And then we just need to make sure this thing is balanced. It looks like in order to balance it, we need to put a 2 in front of each of these things. And actually, we should have balanced it up here, right? Because that's going to be 2 sodium chlorides. Yeah, that balances our equation up here. So if you balance the molecular equation first, the first equation that you write, then that will sort of tell you how to balance the second one as well. Okay, now we can start crossing stuff off. The chlorine, or the chloride ion, doesn't do anything. There's 2 on this side, 2 on this side. Let's get rid of that. Sodium, also a creepy spectator. Let's get rid of those. Okay, and so the only things that we have left here, we've got Ca2+, plus CO3 2 minus, and this gives us CaCO3 solid. Okay? Now, the reason that this is so important, and actually I think your reading says this is one of the most important things, it's because on the AP exam they always ask you to write net ionic equations. You have to do that for every equation that you write in the equation writing section of the test. Okay? So you need to make sure that you split apart anything that is a strong electrolyte, and then you cross out any spectators that don't do anything, okay? Let's see what else we got here. Oh, well, that's it for that. We're going to talk about acids next time. But what I want to show you now is I want to go in real quick and show you, real quick, I say. I hope this is going to be really quick. the chapter 10 on the Ultimate Chemical Equations Handbook, and it actually says this. Well, I thought it said it. Finally, after working through that. Okay, I guess it doesn't say it. I thought it said at the beginning of this that this is the most important chapter in the book. Maybe it says that about chapter 9 because it's leading into chapter 10. But this is a very important chapter, I would say. I would actually call this the most important chapter because you need to know how to write these net ionic equations. All right, so it's talking about overall total ionic. That's what we just talked about. So the only common substances that should be written as ions. This is kind of useful. Okay, so you've got soluble salts, you've got strong acids, and strong bases, and those are the only things that you're going to write as ions in these equations. Okay, everything else you're going to keep together. So soluble salts, that means any ionic compound. Salt is just a fancy word for ionic compound again. That dissolves in water. Any ionic compound that dissolves in water is going to be written as ions. Okay, and then strong acids, same way. If you've got something like hydrochloric acid, HCl, you want to split that apart when you write the equation into H plus and Cl minus. And then strong bases, same way. If you've got something like NaOH, sodium hydroxide, split that apart into Na plus, OH minus. Okay, but that also sort of goes along with the soluble salts. Really, they didn't have to say the strong bases part because strong bases are soluble salts. Okay. Let's see here. What else do I want to talk to you about? Okay, they're just giving some examples here for writing the overall ionic equations. Lots of examples. And basically what you need to remember there is just don't separate anything as a solid, liquid, or a gas. Only separate things that are aqueous. Okay, here. Only separate things that are aqueous and things that are either soluble salts or acids. Okay. All right. Hydrolysis reactions. We need to talk about this a little bit. This is something that may come up at some point, and if you don't completely get this now, that's okay. I'm probably not going to throw a lot of these at you right now, but I do want you to be aware of this. So a hydrolysis reaction here, it's sort of the opposite of an acid-base reaction, okay? So an acid-base reaction, you've got strong acid plus strong base gives you water and a salt, okay? So the hydrolysis reaction is kind of the opposite of that. You've got the salt and you've got water, and that's giving you an acid plus a base, okay? So it kind of happens both directions here. So an example of this, let's say you've got something like ammonium chloride, and you put it in water, okay? And so you've got the NH4 plus here, that's a plus sign, and it's hard to see, and Cl minus, and then you've got water. Okay, so there's your salt, there's your water, and when you put that into a solution, you're actually going to, the OH is going to go with the positive ion there, and you're going to make a base, ammonium hydroxide, and then the H plus and the Cl minus are going to kind of be left there. And really that's an acid because you've got H plus ions running around in the solution. Okay? So that's an example of a hydrolysis. Wanted you to be aware of that. Erase these. See if we've got any good examples here. Okay. Well, there's actually lots of examples, so you can look through this. I do want you to try and read as much of this as you have time for. But really, it's going to be the same basic thing. Now, if you have something like sodium chloride in water, then what you've got there is you're going to have, well, actually, I don't think this is any different than the one before it. Let me see. Oops, went too far. No, I didn't go too far. Sorry. Why can't I find where I was at? There we go, hydrolysis, sorry. Okay, and the reason that this one was different, the NH4OH, it actually is different here, is a weak base. Okay, now we're going to talk more about weak acids and weak bases, and so again, that's why I don't really expect you to know a lot about this right now, but what you might notice here is that when you've got a hydrolysis with sodium Na plus and Cl minus and water, then the water may split apart at that point into OH minus and H plus. Okay. Let's see, what else do I want to tell you about the hydrolysis? I would just read over this, and like I said, I don't think, I mean, basically I just want you to know the term at this point, okay? And the hydrolysis basically is just the opposite of an acid-base reaction, okay? So we talked about acid-base gives you salt and water. The hydrolysis reaction, it's salt plus water gives you acid plus base. And usually, well, I should say always, either the acid or the base is going to be a weak acid or base, okay? Otherwise, it doesn't really undergo hydrolysis. And again, that may not make a lot of sense now. I can try and explain that a little bit more detail in class. But for right now, I just want you to know it's kind of the opposite of an acid-base reaction, okay? All right, I think that's it for now. So again, sorry about the length of this one. Just needed to introduce this stuff and make sure that you kind of understand and remember where we're going with all of this equation writing. We'll talk about acids next time and how they react. So, see you then. Have a good